Welcome to qnawire.
Hi, so over here we have the following problem in which we have 2 point charges which we know the position and a third one with unknown position. We're given the values for the charges of each of them. And we want to find the position of the third charge, knowing that the net force acting on Q1 is going to be -7 in the I direction, because we're told that the magnitude is 7 Newton in the minus X direction. We also know that due to the charges, Q1 and Q2 are going to attract, and Q1 and Q3 are going to attract. So if we want to draw the force of Q2 on Q1, it would be pointing up on the positive X direction. So we know that the net force on Q1 is going to be equal to the sum of the forces of charge 2 on Q1 plus the force of Q3 on Q1. First thing that we're going to do is to find the magnitude of the force of Q2 on Q1. And we also know that this is equal to -7 Newton in the I direction. All of these are going to be vectors. So the magnitude of the first vector is going to be equal to k times Q2, Q1, all of this in absolute value, divided by r squared. The distance in between these two guys is equal to 0.9 meters as given in the problem, and the value for Coulomb's constant is 8.99 times 10 to the 9 Newton meter squared over Coulomb squared. This corresponds to 1 over 4 pi epsilon 0. The value for Q2 and Q1 are respectively 5 and 3 millicoulombs. So we're going to get 5 times 10 to the minus 3 millicoulombs times 3. Sorry, in this case, coulombs directly, because the times 10 to the minus 3 factor accounts for the conversion of millicoulombs to coulombs, times 3 times 10 to the minus 3 coulombs. In this case, I'm getting rid of the sign of the charge because of the absolute value function. And the distance that is going to be 0.2 meters squared. The magnitude of this force is equal to 3,371,250 newtons. Now, what is going to be the direction of the force? We know that this is going to be an attractive force, and in this case, as we can see on the diagram, it is going to be on the positive X direction. So this is going to be on the I direction. So now the net force on Q1 is going to be equal to, we know that this is -7 Newton in I direction, and this is going to be equal to this very big number in I plus the force of charge 3 on charge 1. This is going to give us the direction that we are going to have for charge 3. The vector of Q3 on Q1 is going to be equal to minus 3,371,250 newtons in I minus 7 newtons in I. So this is going to be equal to minus 3,371,257 newtons in the I direction. So that means that in our original diagram, for this force of Q3 to happen, then Q3 needs to be on some position over here on the positive X direction. So now that we know that that is going to be true, what we're going to get is, that it would be on the negative direction, right? Because we want the force to be negative, so Q3 needs to be somewhere on over here. For the force, let me write down the vector here. So for the force of Q3 on Q1 to go on the negative axis. So this is going to be towards the left. So we can calculate that value of the distance using, again, Coulomb's law. Q3 Q1 over r squared. Now the value for r is going to be equal to the square root of k times Q3 Q1 in absolute value divided by the magnitude of the force of Q3 on Q1. And we know that this is going to be on the negative x direction. So this is going to give us r equal to square root 8.99 times 10 to the 9 Newton meter squared over Coulomb squared. The charge of 3, which corresponds to 8 millicoulombs, so 8 times 10 to the minus 3 coulombs, times the charge 1, that is 3 times 10 to the minus 3 coulomb. Remember, I'm not taking into account the signs because I'm using the absolute value, and the absolute value of the force, that is 3,371,257 newtons. Coulombs are going to cancel out with Coulomb squared, Newton with Newton, and meter squared, as we take the square root, is going to give us our result in meters. So the distance is equal to 0.25 to 98 meters, which is approximately 0.253 meters. So our full diagram is going to be Q3 at minus 0.253. Next, we're going to have Q1 at 0 meters. And finally, Q2 at 0.2 meters. And the diagrams of the forces are going to be the following. Q1 is going to experience attraction towards Q2, force Q2 on Q1, and it is going to experience as well attraction, but a little bit stronger, corresponding to Q3 on Q1. So this is going to be the final result. Thank you very much and have a good one. Just a comment, if you want to get a more accurate result, you can put more significant figures on Coulomb's constant over here. So you can replace this value with the one that was recommended by your professor, or if you want to get use of the full result, you can also employ that, but the procedure is going to be exactly the same. So, have a good one.